All right, in this video we're going to introduce rational functions and their graphs. So a rational function is a function in the form p of x over q of x, where p of x and q of x are polynomials. So for instance, we might have something like 5x plus 3 over x squared minus 7x plus 10. So we took a look at what qualifies a function to be a polynomial in our section on polynomial functions. So here we're just going to put one polynomial over another polynomial. And we're going to start by looking at end behavior or long-term behavior of a rational function. We're going to split this objective up into two separate videos just for time purposes. So recall from polynomial functions that end behavior refers to the graph's behavior as x approaches infinity, or as x keeps going further right, and also as x approaches negative infinity, or as x goes further to the left. So in other words, what are the output values approaching as our input values get larger in either direction, both very large in the positive direction, where x's are going to the right, and our inputs also getting very large in the negative directions, or where x is going to the left. So with rational functions, for our end behavior, one of two possible scenarios is going to happen for every single function. Either the function will look like a horizontal line for its end behavior, or it won't. And that's really your only two options. Either it's a horizontal line, or it's not a horizontal line. It's something else. So example 1, we're going to determine the end behavior of the function f of x equals 2x over x squared minus 3. And again, for a numerical approach to determining end behavior, we can plug in values of x that are very, very large, both in the positive and negative direction, and take a look at what happens to our outputs from there. So if we keep putting in larger and larger positive values for x, for instance, 1,000, 10,000, all the way up to 1,000,000, notice our output values here are getting closer and closer and closer to 0. They're actually diminishing in value the higher the value of x goes. And that's because this x squared down here has way more of an impact than the 2 times x up in the numerator, especially when we start getting into very large values. So, for x equals 1,000,000, our denominator is 1,000,000 squared, and then minus 3, which is a very, very, very large number. For heading in the negative direction, as x approaches, you get negative 1,000,000 here, our outputs are getting very, very small as well. They're also getting close to 0. So they're just getting closer to 0 coming in from the left-hand side on the x-axis. So notice our outputs, again, are getting closer and closer to 0. So the end behavior of the rational function for f of x equals 2x over x squared minus 3 is 0. It's 0 as we head to the left, where we were putting in larger negative numbers for x. And it was also 0 as we were heading to the right, where we were entering in larger positive values for x. So essentially, what end behavior is visually is, if we were to graph f of x equals 2x over x squared minus 3, as we zoom out of that graph, our graph is going to look more and more like the graph of the line y equals 0. So for instance, here's our function, 2x over x squared plus 3. Right around here we got a little bit of interesting behavior, but long-term end behavior, as we go further to the right and as we go further to the left, our values of x, or our output values of y here, just get closer and closer and closer to 0, like 2.94 and negative 0.25. But as we zoom out further and further, notice we're losing that sort of interesting behavior around the origin, and now it looks just like a flat line, like y equals 0. In fact, if we really zoom out pretty far, we might even be able to get so decimals can only hold so many place values for a decimal. So here at 16,100, it doesn't have enough storage capacity to put that decimal, so it just gives you back a 0 as a rounded answer. So As far as the notation goes, we would say that the limit as x approaches negative infinity of our function is 0. So remember, this is as we head further to the left on our graph, our output values are getting closer to 0, and the limit as x approaches positive infinity of f of x is also 0. Or as we head to the right, our function is approaching 0 as well. All right, so that about does it for this video. Thanks for watching. We'll look at some more examples in the next one, and I'll see you.